All right, we're getting close to the end here. Class 30, after today we will be 75% done with the semester, just 10 more days of class. Class 40 will be the last class. It's getting close. You know, it might seem long right now, but by the time we get there, we'll be looking back and saying, well, that went kind of fast, I think. That's the way I feel. In the meantime, we have, yes, a test you know about on Friday. For this class, we again will remember that we'll start at the scheduled time of 9 o'clock instead of 9:05, and you can go till 10:45. And those of you who are on the online class, again, you have these different options, and most of you have already contacted me about what option you want. Officially, the sections covered are this group, though I've told you the types of problems to expect, and they turned out to be none from section 3.8 with the three-dimensional system. But there could be, for future people who are watching this video maybe 10 years from now or something, there could be a question from 3.8 for you. In chapter 5, you've only had problems through section 5.1. That's the linearization. We'll do more examples of that today. Section 5.2 continues that and talks about nullclines. We've already talked about nullclines, though, starting back in chapter 2, I think. So that's the main new thing for section 5.2. On the problem on the test where you have a interacting species model, it could be predator-prey, it could be competing, it could be cooperating. One thing I will do to make your work a little easier is I will have Mathematica draw in the vector plot for you. In other words, really the direction field for the system. That will help you get the directions of solutions correct, though there will be perhaps some subtle points you'll have to watch out for. For example, how do you cross nullclines? As well as looking for what are called separatrices, possibly. I'll do an example where I show you what I mean here in a few minutes. On the final exam, it'll be a little bit more challenging because you'll have to do it purely by hand. You'll probably have to draw the nullclines yourself, and also there will be no vector field shown to you, so you will have to try to get the directions of solutions accurately on your own, and so it'll be tougher for the final. It's definitely an art form that takes a lot of practice to get good at drawing phase planes for nonlinear systems. That's something big to work on between now and the final exam. So let's do an example. Way down here, we thought about a predator-prey system already. Let's go down and let's consider a competing species model. You might want to write down that system there. It is competing species. X and Y are competing against each other. The interaction terms for both are negative coefficients. In the absence of the other species, both X and Y are following a logistic model. When Y is absent, X follows this, and the equilibrium values of X are going to be 0 and 150. When X is absent, when X is 0, this term goes away in the dy dt equation, and Y has equilibrium solutions at 0 and 100. As far as finding equilibrium points, I'm actually going to make it a little easier for you on the test there as well. You won't have to find equilibrium points. But I'll tell you what they'll be. But you certainly should really be able to. There's the right-hand side of the dx dt equation. I'm calling that little f of xy. Little g of xy is going to be the right-hand side of the dy dt equation. To find the equilibrium points, factor as much as possible. In this case, you can factor out a common factor of x in the top equation and y in the bottom equation. What's left over from the top equation after you factor out an x? Well, there's the 150 minus x there. And factor an x out of that, you're left with a minus 3y. Then this one, factor out a y there, you're left with 100 minus y, but also a minus 2x. If you set these equal to 0, and solve for the solutions of that system of algebraic equations. Those are going to be the equilibrium points of the differential equations, the system of differential equations. Okay, so how do you think about solving a nonlinear system like this? Well, certainly 0, 0 is an equilibrium point, which again makes sense in these interacting species models, because if you don't have any species, then they're not going to magically appear. At least in the model. Of course, in real life, they could move into the region you're thinking about. So x equals 0, y equals 0 is certainly an equilibrium point. 0, 0. If x is 0, the top equation will be 0. And y doesn't have to be 0 to make the bottom equation 0. It could be 100. If you plug in x equals 0 there, you get 100 minus y. That will be 0 in that case when y is 100. So 0, 100 is an equilibrium point. If y equals 0, that makes the bottom equation 0, but the top equation doesn't, in the top equation, x doesn't have to be 0 to make it 0. If y is 0, then this part will be 0 when x is 150. There's one more equilibrium point when x and y are non-zero, both non-zero. These two things could be 0. That's a system of linear equations that you can write in an alternative form like this. X plus y, 3y equals 150, and 2x plus y equals 100. Setting each of these things equal to 0 and rewriting it. That system of linear equations can either be solved by elimination or substitution. Let's solve it by substitution. You can take the second equation and solve it for y as a function of x. Y is 100 minus 2x. Substitute that into the first equation in place of the y. And now that's a linear equation in x that can be easily solved for x. Distribute the 3 through the parentheses. I'll swing the x's on the other side because you get a negative 5x on this side. Add 5x to both sides. Subtract 150 from both sides. 150 divided by 5 is going to be 30. Looks like x has to be 30 at an equilibrium point. Find the corresponding value of y now by substituting back into there. 2 times 30 is 60. 100 minus 60 is 40. Looks like our last equilibrium point is 30, 40. And that's the most interesting one, right? These other ones correspond to one of the species or both being extinct. This one's the interesting one. Solve can confirm our answer on Mathematica. Here's the equilibrium points. What I'd like to try to do now is I would like to try to make my work harder than your exam will be. I'd like to try to draw the nullclines in, and also try to draw solution curves without seeing the vector field, without using vector plot. I will eventually use vector plot. It's going to be tricky, okay, but that's something to work on. I'm making it harder on myself here than the exam will be for you. We'll eventually check our answers, though. We'll use the linearization technique as well with the Jacobian matrix. Focused on the first quadrant. Let's draw the nullclines in first. The nullclines, you think about where these things are 0 as well, each individually. The top expression there, the right-hand side of the dx dt equation, will be 0 either when x is 0 or when this is 0. X will be 0 along the y-axis, so the y-axis is part of the x nullcline. The x nullcline is where dx dt is 0, so solution curves are vertical, straight up or straight down. They cross with a vertical tangent if the nullcline itself is not vertical. But this nullcline is vertical, so solutions that start on this nullcline stay on the nullcline. In fact, we know 0, 0, and 0, 100 are equilibrium points. And it should make sense that essentially, if you think of that as a phase line, that your arrows should look like this, based on what we know about logistic lines. How could that be checked? That could be checked with the dy dt equation. Maybe I should have put the dxt and dy dt here. Is the sign of dy dt positive or negative when y is in these various regions? And x is 0. Look at this equation, substitute in x equals 0, that term goes away. You're only left with that thing. That's an expression that, thought of as a function of y, will have a graph that's an upside down parabola. Right, it's quadratic in y. Intercepts at 0 and 100. It's going to be positive when y is between 0 and 100 and negative otherwise. Just like solutions are going up, increasing when y is between 0 and 100 and decreasing otherwise. I probably shouldn't draw the arrows on the axes. That could be confusing. Likewise, we can think about what if, well, that's one of the x nullclines. Let's focus on the simple y nullcline. That's when y is 0. That's the x-axis. That's a y nullcline. It's horizontal. Solutions that start on it have to stay on it. The vectors in the vector field are going to be horizontal along that line. You're going to have an equilibrium point at 150, 0, and it's logistic, just like the one for y is. So your arrows are going to look like that. All right, let's draw the more complicated nullclines. Thinking about the x nullcline again, set that equal to 0. The graph of this equaling 0, 150 minus x minus 3y, is going to be a straight line. You actually don't have to solve for y to draw it. You can think about what its x and y intercept are just by looking at this equation. Its x-intercept, where y is 0, is going to be at 150. If you plug in y equals 0 here, x is 150, which makes sense. That's an equilibrium point. And its y-intercept is going to be at 50, okay, which maybe doesn't make sense. If x is 0, y is 50, not 100. That's okay, it's not wrong. This is going to be part of the x nullcline, the other part besides the y-axis. Solution curves have to cross this with vertical tangents. Draw a bunch of little vertical tangent lines. These are going to be tangent lines to solution curves. It's not clear yet whether solutions go up or down as they cross. You have to think about the sign of dy dt to decide that. That is the other x nullcline. What about the other y nullcline? Set that equal to 0. Find its x and y intercepts, or think about it in terms of that equation there. It's a line with a slope of -2 and a y-intercept of 100. So its x-intercept is 50. That's the other part of the y nullcline. Solutions cross that horizontally. Where distinct nullclines, x and y, cross, you have equilibrium points. There's no equilibrium point there because that's a crossing of an x nullcline with another x nullcline. It's not a y nullcline. There's no equilibrium point here because that's a crossing of a y nullcline with another y nullcline. Where dy dt is 0. dx dt is not 0 there. Right there, that's a crossing of two different kinds of nullclines, an x nullcline and a y nullcline. There's your fourth equilibrium point. That's the point 30, 40. Seems pretty clear that the equilibrium point at the origin, if you think about also including negative values of x and y, which is not realistic, but just for the sake mathematically of thinking about the origin there, seems like it's going to be a source. Is that true? linearization can help us check. To linearize the system near the origin, it's good to not have it in factored form, but to expand it out. Go ahead to the first equation and multiply x through the parentheses, and don't write it like this. Instead, write it like this: 150x minus x squared minus 3xy. Do the same with the dy dt right-hand side. Get 100y minus y squared minus 2xy. When x and y are both close to 0, when you're close to the origin, these are well approximated by throwing away the nonlinear terms, only considering the linear terms, the 150x and the 100y. I forgot to write on the board the other day that this approximation is good when your point is close to the origin. Being kind of fuzzy here, not being real precise about this. How good are these approximations? It's a little funny because all these quantities are small when x and y are close to 0. But x squared, y squared, 2xy, 3xy are orders of magnitude closer to 0 than x and y themselves are. You might be thinking, well, yeah, maybe it's also because the 150 and the 100 are so big, but that's not something to focus on. The thing to focus on is what is the order, so to speak, of the terms. First order terms, linear terms. Second order terms, those are quadratics. Second degree might be a better word to use. And in other words, there's a corresponding linearized system. Emphasis on being linearized near xy equals 0, 0. dx dt equals 150x, and dy dt equals 100y. That's a different system than the original, but it's related to the original. We always do this relating thing. Remember with, for example, forced second order equations, we consider corresponding homogeneous equations and corresponding complexified equations. This is a corresponding linearized system. It's not the same as the original system, but it's related. You could write this in vector form as d capital Y dt is a matrix 150, 0, 0, 100 times capital Y, where capital Y is little x, little y. And that's a diagonal matrix. Diagonal matrices have the property that their eigenvalues are right along the main diagonal. You can see they're both positive numbers there. Therefore, the origin for that system is a real source. By the Hartman-Grobman theorem, which is not mentioned in your book, and by the way, that is the right name. I looked it up to check. The Hartman-Grobman theorem, that means the original system also has a source at the origin. The linearization, the linearized system, tells you information about the original system near the given equilibrium point. There are some cases where it doesn't work. In a nutshell, those cases are when the eigenvalues of the matrix there, which actually is the Jacobian matrix actually, here, when they have zero real part, meaning they're either the number 0 or they're purely imaginary. When that happens, then the linearization doesn't necessarily help, except in certain special cases, like something called a Hamiltonian system we'll see later. But we're not encountering those special cases yet. We're considering cases where the real part of the eigenvalues is non-zero. Here, both eigenvalues are real numbers, so their real parts are also real numbers. Well, they're always real numbers, but the real part is the same as the value of these real numbers. It's 150 and 100. It's a source. like we could predict by looking at the picture. How do you linearize near the other points? You can't just throw away the nonlinear terms like I did here, because that only works because of this fact right there. These approximations are only good when your point is close to the origin. There's two approaches you can take. The book does discuss both of them. You could essentially translate your axes so that the origin occurs at the given equilibrium point under that translation. Effectively, it's a change of variable. Or you can use the Jacobian matrix. For the sake of time, we'll just focus on the Jacobian matrix here today, because that's what you need to do for the test. Maybe I'll have Mathematica do the translation idea briefly to show you. After the test next week, I think we'll try an example by hand where we translate. So you calculate this Jacobian matrix, call it J for Jacobian, in honor of Jacobi. It's a matrix of partial derivatives. The derivative of the top right-hand side function with respect to the first variable is the upper left entry. The derivative of that top right-hand side function with respect to the second variable is the upper right entry. Do the same derivatives for the second right-hand side function, g. That's the Jacobian matrix in general. This is a function of x and y. It's a matrix-valued function. It's a function whose output is a matrix. Weird. But we're used to weird things in here, aren't we? You can do that. You can have a matrix-valued function. How do you find these partial derivatives? Just like you would guess you would do if you had to guess if you never knew. There's the formula for f in expanded form. That's the nicest way to have it here as far as taking these partial derivatives. Differentiate that with respect to x first, treating the y like a constant. 150 minus 2x. Treat the y like a constant here. Differentiate with respect to x. What do you get? Minus 3y. It's easy to make a mistake, but if you're real careful, you know what to do. 150 minus 2x minus 3y. Now differentiate with respect to y. Treat the x as a constant, so when you differentiate with respect to y, that becomes 0, 0, negative 3x. It's the upper right entry. Differentiate g with respect to x. Treat the y like a constant. Get 0, 0, negative 2y. Then differentiate g with respect to y, treat the x as a constant, get 100 minus 2y minus 2x. There's your general Jacobian matrix. It's a function. How is it relevant? You evaluate this Jacobian matrix at the equilibrium points to find the corresponding linearized system. Let's evaluate it at this one. You should be able to evaluate it at any of them. You can just in our mind evaluate it at the origin. If you evaluate it at x equals 0, y equals 0, you'll get 150, 0, 0, 100. Same thing as that. What about at 30, 40? Let's do it there. I'm going to write down the corresponding linearized system near 30, 40 here after I find the Jacobian matrix. Evaluate it at 30, 40. Plug in x equals 30, y equals 40. 2 times 30 is 60. 3 times 40 is 120. 150 minus 60 is 90. Minus 120 is negative 30. Take a second to check my work there. I will as well. look good. Negative 3x is negative 3 times 30 is negative 90. Negative 2y is negative 2 times 40 is negative 80. And 100 minus, okay, I did it that order carefully here. It doesn't matter because they both have a negative 2 in front of them. 100 minus 80 minus 60 is negative 40. Don't be deceived by the fact that all the entries of that matrix are negative. That doesn't mean it's a sinc, necessarily. Could be. You either have to find the eigenvalues of this and see are they both positive, both negative, one positive, one negative, are they complex? Or probably more quickly use the trace determinant plane. The trace is negative 70, negative 30 plus negative 40. The determinant is negative 30 times negative 40, positive 1200, minus negative 80 times negative 90, minus positive 7200, negative 6000. Are the eigenvalues going to be both positive, both negative, one positive, one negative, or complex? You should be able to tell right away based on the trace and determinant. In fact, all you need to look at is the determinant. In the TD plane, it's going to be a saddle point. TD, you're below the t-axis, D is negative, you get a saddle point. That's the easiest case. The Jacobian matrix has one positive, one negative eigenvalue. You could find the eigenvalues also to confirm that. This is quicker. That means the corresponding linearized system near 3040 can be written as follows. I'm going to use a different letter here. Other than capital Y, I'm going to use a capital U. Why am I using a different letter? To emphasize, for one thing, that it is a different system. It's not that I couldn't use a capital Y, but I want to emphasize it's a different system. And when we talk next Monday about translating the origin, so you have new variables, I'm going to call those variables little u and little v, just like the book does. And so capital U is going to be a vector whose components are little u and little v. The corresponding linearized system is this. And I'm going to want you to be able to write it this way in the test. I'm going to ask you to write the corresponding linearized system with this capital U in fact. This right-hand side function is a linear function of U. It's a matrix times a vector. In fact, on the test, I'm also going to call this capital L of capital U vector vector. It is a vector field. In fact, when I write the question, I'm going to just say, find the linearized system du dt equals L of U, and it's up to you to find the formula for L of U. Well, it's the Jacobian matrix times U. It's not that hard if you know what to do. And I'm telling you what to do right now. It is a linear function of U. That's how it's going to be phrased in the test. For future people, it won't necessarily be phrased that way for you. You might have a different problem. But for this year, that's the way it's going to come up on the test. So do be able to write the linearized system. You can also just focus on the Jacobian. Note that it's got, in this case, one positive, one negative eigenvalue. The origin is a saddle point for this system in a UV plane. By the Hartman-Grobman theorem, that implies this point is a saddle point in this xy plane. What about the corresponding eigenvectors? Well, you're not going to have to find those, and in fact, you won't need to because, again, I'll have the vector plot in there. But let me just show you the corresponding eigenvectors here for this matrix and see if they make sense in the context of the phase plane. Let me type in that Jacobian matrix, negative 30, negative 90, negative 80, negative 40. Let's do eigensystem for that. Yep, one positive, one negative. Negative 120 and 50. Eigenvector corresponding to negative 120 is 1, 1. Eigenvector corresponding to 50 is negative 9, 8. 1, 1 points in this direction. 45-degree angle. That means you can interpret that in terms of the nonlinear phase plane as being almost straight line solutions in this kind of direction. Not exactly straight line solutions, because the linearized system is just an approximation for the nonlinear system. But near that point, it's almost like you've got a straight line solution for the negative eigenvalue, like that, and so you've got arrows heading toward that point. You'll see with the vector plot that the arrows point that way as well. And the other eigenvector, negative 9, 8, points approximately like that, approximately at a 135-degree angle, not exactly. There's almost a straight line solution like that, a line of solutions. It's not exactly right. It's not a straight line solution because this is a nonlinear system. The linearized system just gives you an approximation, but it's almost going to match what happens. They're going to look straight, as far as you can tell. Until you get further away from the equilibrium point, and you'll see that solutions end up going up there and down here. And if you cross the nullclines correctly and you look at the vectors in the vector field, other solutions look like this. And you'll see that by looking at the vector field. Again, on the final exam, you will not have the vector field shown to you. You will have to draw on the other solutions without the benefit of the vector field in the background. You can see I'm crossing the nullclines correctly. That's what solutions are doing. There are 4 special solution curves that are called separatrices. Separatrix is singular. Separatrix, I think that's spelled right. Separatrices is the plural of separatrix. There's 4 very special solutions that separate solutions that behave differently from each other. That's why they're called separatrices. They separate solutions, in this case in the first quadrant, because that's what we're focused on, that behave differently. There's a solution going essentially from this equilibrium point toward this one. Does it actually touch the equilibrium points? No, it doesn't. It's just asymptotic to them. It approaches this equilibrium point as t goes to plus infinity, and it approaches that equilibrium point as t goes to minus infinity. But you draw it as if they connect them. That's one separatrix. It separates solutions here from solutions there that have different long-term behavior. These solutions head toward that point, these solutions head toward that point. There's another separatrix that I haven't really drawn except for this part here. If you follow this one backward in time, now go forward in time, the arrow goes in this way. It looks maybe like that. I'm just guessing. I suppose it could look like this, for all I know. Looks like this or this, perhaps. Maybe it looks straight for all you can tell, even though it's probably not straight. But it goes in toward the origin. Let's just pretend it looks like this. We'd have to look at the vector plot to see more carefully. That's a separatrix as well. Solutions on either side of that, and still above these separatrices, head toward these equilibrium points as t goes to infinity. There's 4 separatrices. This solution curve that I'm just guessing might look like that, and 2 solution curves that look like this and this. They separate the first quadrant into 4 subquadrants, curved subquadrants, that have different kinds of limiting behavior for solutions. Solutions down here for initial conditions in here head to that point as t goes to plus infinity, and this point as t goes to minus infinity. Solutions with initial conditions in here head to this point as t goes to plus infinity, and this point as t goes to minus infinity. Solutions in here head to this point as t goes to plus infinity, and off to infinity as t goes to minus infinity. And solutions with initial conditions up here head to this point as t goes to plus infinity, and off to infinity as t goes to minus infinity. These four solutions, these separatrices, have other properties. This one and this one approach that point as t goes to plus infinity, and they don't deviate away. This one goes to the origin as t goes to minus infinity. This one goes to that point as t goes to plus infinity, and to this point, the saddle point, as t goes to minus infinity, whereas this one goes to this point as t goes to plus infinity, and again back to the saddle point as t goes to minus infinity. And again, one more time for emphasis, they don't actually touch the equilibrium points, they just approach them. If they touched them, that would violate uniqueness. They're asymptotic to them. Limiting behavior is what we're talking about here. The overall moral of the story for this competing species system is it's plausible when you have competing species that one species could die off. That's sort of the moral of the story here. You shouldn't take this too literally in terms of exact quantitative predictions, or even necessarily that one or the other species could die off, or will die off, I should say. But the moral is one of them could die off. And moreover, it's a sensitive dependence on initial conditions. Think about initial conditions on either side of that separatrix. Solutions just to this side cause y to go away and x to thrive, and solutions with initial conditions just to that side cause x to go away to 0 and y to approach 100, to thrive. I don't know if thrive is the right word there. So it's a very sensitive dependence on initial conditions near the separatrices. That's kind of another moral of the story. Depending on the initial conditions, that can definitely have a big effect on the future. What does the vector plot look like? Question?
Yeah. Two quick questions. So on the equilibrium point 30-40, you had said that you drew the arrows and you just said from the vector field. How would you do that without the vector field?
It's difficult. I don't want to get into it right now for the sake of time.
And then what for you over there? What is that components of, like x, y? Are they translated coordinates?
Capital U, what I said is really going to have components I'm going to call little u and little v next Monday. Okay. And essentially, those are translated coordinates. I'm going to create a new coordinate system with origin at that point. I'm going to call that a u-axis and not a v-axis. But you don't have to worry about that. Do be able to write down the corresponding linearized system near the given point using this notation, though. There's what the vector field looks like. For all you can tell, it looks like this separatrix is straight. I'm sure it's not. It just looks are deceiving. The one that would come from up here and down to this point. You can see you're crossing the nullclines in the way that I drew. We can also get the stream plot in there to see the solution curves themselves. Whether you're on a separatrix or not is very sensitive. This solution curve, for example, is close to the separatrix. It approaches that saddle point pretty closely before veering away. In fact, it's probably, as a practical matter, impossible to find initial conditions that are exactly on the separatrices. That's probably impossible if I had to make a guess about it. You pick an initial condition, in all likelihood, with probably 100% probability, you will not have picked an initial condition exactly on the separatrix. And so when you get Mathematica to draw it, it's very hard to get it to draw separatrices. You have to experiment with initial conditions, and even then you're only getting approximations to the separatrices. But they do exist, which should make some intuitive sense. Okay, that's the most important thing to review, I think, for the bulk of our time today. We only have 10 minutes left to talk about the other kinds of problems for exam 3. But I think these are definitely easier based on things we've done already. I mentioned there's a derivation that you're going to have to do using the quadratic formula. to find either conditions on P and Q for a simple harmonic oscillator, or on M, B, and K to have either overdamping, critical damping, or underdamping, so you should know what those terms mean as well. So the differential equation, I'm going to, just for sake of time, write it with prime notation here. The differential equation could look like that. It could look like this. This is how you'd write it initially with M, B, and K. Okay, there. I could divide everything by M. No matter how I write it, you should be able to use the quadratic formula to help you figure out what conditions on M, B, and K, or P and Q give you overdamping, critical damping, or underdamping. It involves thinking about the characteristic polynomial, which you can get without going to a matrix form. You don't have to go to a matrix form to write down the characteristic polynomial, right? You know that. For example, with this form here, you write the characteristic polynomial. It doesn't matter whether you use lambda or s. Typically we've used s when we've thought about it in scalar form, but you could use lambda too. And you think about the roots of that, the eigenvalues. Second type of problem is to write the characteristic polynomial of an arbitrary matrix, little a, little b, little c, little d, in terms of its trace and determinant. If you don't remember what the trace and determinant are, I'll let you look those up. I'll let you think about this. You've got to think about finding eigenvalues and how you find eigenvalues to help you find that characteristic polynomial. I'm not going to write it down. That's for you to think about. Period and frequency of the fast oscillations and the slow oscillations, or beats, for undamped forced harmonic oscillator. With the right-hand side, that's a cosine omega t, or a sine omega t, I should say. So the forcing function is sinusoidal. Whether it's cosine omega t or sine omega t, you should know the formulas for how to find those periods and frequency. I did talk about it in class. So if you didn't write it down in your notes, you'll want to go back and look at some of the videos. Also, in the solution key to the problems where you have to do that kind of thing, I wrote the general formula as well. The book does a particular example for a particular value of q when they think about it. Just mention where that is. They use complex exponentials to do the analyzing, and their analysis to think about the beating phenomenon. Let's see, section 4.3, yeah, okay. It's on page 418. That entire page essentially is their analysis using complex exponentials to think about the beating phenomenon. But they do it for a particular value of q. They pick q to be 2. In class, we did an arbitrary q. And you should be able to deal with an arbitrary q. You look at an undamped force harmonic oscillator equation. Oh, okay. Oh, that's wrong. Think about the square root of q and omega being close. Okay, you should be able to think about an equation like that and find the period and frequency of the fast oscillations and the slow oscillations. Be able to quickly identify a given system as having, well, I'm telling you it's going to have infinitely many equilibrium points. There's a real quick way to do it. Calculation that takes you about 10 seconds. I won't say what it is. I have said it before. There's also a verbal description you can give based on the nature of the entries of the matrix, or when you're going to have infinitely many equilibrium points. That will also affect the eigenvalues. There's going to be a special eigenvalue when you have infinitely many equilibrium points. You should be able to find them, find eigenvectors, find the general solution, and solve an initial value problem. And the method is just like the method from previous sections. You find the eigenvalues, the corresponding eigenvectors, they're going to be linearly independent. You take a linear combination, k1 e to the lambda 1 t, v1 plus k2 e to the lambda 2t times v2. Still the same overall idea when you've got these linearly independent eigenvectors. You can write a general solution like that. I'm assuming when I write that the lambdas are real. They won't be complex when you've got infinitely many equilibrium points.
How do we know if they have infinitely many equilibrium?
I'm not telling you right now. That's something that I did tell you earlier.
Oh,
You can look it up.
How-
Section 3.5, it'll be helpful to look at the section.
3.5.
Okay, it's a pretty easy condition, actually. I'm letting you look that up if you don't remember. There's going to be an initial value problem that's an unforced harmonic oscillator. The eigenvalues could be real or complex, be able to handle both cases. You know, what happens with unforced equations when you have complex eigenvalues? And again, you don't have to bother thinking of it in vector form with a matrix. You could, but you don't have to bother. You can just, well, I erased it, but I'll rewrite it. You can just think about that as your characteristic polynomial right away. If you at least, if it looks like that to begin with, divide everything by m first. That's p, that's q. What if the eigenvalues there are complex? Well, they are going to be complex conjugates of each other. I think I hadn't mentioned that in class. I probably should have. When you've got these real differential equations and you have complex eigenvalues, they're going to be conjugates of each other. You should have noticed that. You always get alpha, something plus or minus something times I. You only have to consider one of those, say the plus. Consider this complex solution. With Euler's formula, it ends up equaling e to the alpha t cos beta t plus I e to the alpha t sine beta t. That is a complex solution. That's not a general solution of the original equation. Not. But you can use it to find a general solution. There's the real part. There's the imaginary part. Exclude the I. Put a k1 in front of the real part. Add a k2 times the imaginary part. Don't put the I in there. And there you have a general solution of the original homogeneous equation. That is going to work for corresponding the homogeneous equation for forced equations. Let's go down here a little bit. I guess it's right here. Given a forced damped harmonic oscillator, you are first going to have to find the corresponding homogeneous equation and then find the corresponding YH. H standing for homogeneous. That's going to be part of your general solution. That helps you solve initial value problems. Then complexify the equation and find YC. A e to the I omega t. Find A. A helps you find the amplitude and phase angle of the forced response. The amplitude of the forced response, the YP, is the modulus of A. Let's say we have the complex plane here. Let's say A is right there. The length of that line segment, the modulus of A, is the amplitude of the forced response as a function, as a sinusoidal wave. That's kind of amazing. The length of that line segment is the amplitude of the sinusoidal wave, the YP, the forced response, the steady state solution in the damped case that all solutions approach because of the damping. And the angle here, called a phase angle, also called the argument of the complex number A. The length there is also called the modulus. That's the phase angle. That tells you about the horizontal shift. Turns out YP can be written as capital A times cosine omega t plus phi. And it always turns out for our examples that phi is a negative angle either here or here, you should know that if it happens to be over here, when you use the formula to find it involving the arctangent, you're going to have to subtract pi from it. Because arctangent always gives you an answer in the first or fourth quadrants. If the angle happens to be over here in the third quadrant, the arctangent of the y-coordinate of that point divided by the x-coordinate of that point is going to be an angle up on the first quadrant, a positive angle. Subtract pi from that to get this angle, this negative angle there. That's always what happens in our examples, is the angle ends up being in one of these quadrants. Meaning you're adding phi, but you're really subtracting a positive number there because the number there you're adding is negative. It's always corresponding to a rightward shift. Real quickly, we're about out of time. You should be able to maximize the amplitude of the force response as a function of omega. I will give you a specific P and Q. Okay, it's just a calculus problem. Differentiate the function with respect to omega, set the derivative equal to 0, solve for omega, and also be able to find the maximum value itself by plugging the critical point into the function. It's just a calculus problem there. Easier than the type that came from section 4.4, that homework assignment with 3 problems that were very long, okay? Easier than those problems, but of a similar spirit. There is a bifurcation problem, a 1-parameter family of linear systems depending on a parameter A. Find the trace and determinant, graph the parametric curve, which is not a solution curve, it's just telling you information about the systems. There's going to be some curve in the trace determinant plane. When you cross the critical loci, then you have bifurcations. You should be able to identify the different behaviors in the different regions, as well as along the critical loci themselves. I'll give you options, actually, to make it easier. Identify behaviors, find bifurcation values. Thinking like an analyst, not topologist, meaning making a distinction between spiraling and not spiraling. That's an important distinction for us. When you cross the repeated loop parabola, we're considering that to still be a bifurcation. A topologist would not, okay? Because to them a sink is a sink whether it's spiraling or not. But to an analyst, the distinction between spiraling and not spiraling is important. And then here's the problem about the Jacobian matrix. So that briefly covers everything. If you study these things, you should do fine. You need 1 note card front and back, and you use your calculator. See you Friday at 9 o'clock.